Maybe that's a better theme song. I don't know, but welcome to AP Chem Video. It's me again, and we're going to continue on with these KSP notes. So, let's see here. We left off on example 5, and I asked you to go ahead and complete that table and calculate the solubility for each of those salts. Okay, now what I want to talk about is which one of these salts is most soluble. So if you go ahead for the first set, they have something in common. There's one cation and one anion. One cation, one anion. The cation and anion are all in a 1-to-1 ratio, so their KSP expression can be represented the same way as x squared. So when you solve for x, you see this relationship. So the most soluble salt of the first 3 is the bottom one, the calcium chromate, and then the copper chloride, and then the barium carbonate. What I want you guys to see is the same trend true with the KSP. So if you look at KSP, this bottom guy has the largest KSP, which means that it goes the most in the forward direction. So you'd think it'd be the most soluble. And as it turns out, it goes in order, 1, 2, 3. So what you could say is that, okay, the higher the KSP, the more soluble the salt. But that doesn't always work. So when you look at the second set, they're not in 1-to-1 ratios, is basically the difference, the cations and the anions. So when you solve, you got some really different things going on here. So when you solve for x, remember x tells us how soluble that substance is. How many moles of that salt are dissolving per liter. And as it turns out, it looks like the top one here, the silver phosphate, is the most soluble. Okay, and that's followed by the nickel hydroxide and then the silver bromide. Well, do you see the same trend with KSP? If you look at these numbers, well, the bottom one actually has the largest KSP. So you think that that one's the most soluble. But just because of the fact that the cations and anions aren't in the same ratio, it doesn't work out that way. You just got some different things going on with the math. So, long story short, if you're comparing salts that have the same number of ions, whether it's 2 ions, 1 cation, 1 anion, or 3 ions in total, does not matter. You can just look at the KSP. The bigger the KSP, the greater the molar solubility is going to come out. Now, if you're comparing salts that do not have the same number of ions, like these examples right here, you cannot just look at the KSP and know which one's going to be most soluble. You have to calculate the actual molar solubility like we did right here. So basically what I'm telling you is sort of a shortcut that you can take depending on if you recognize that the salts you're comparing have the same number of ions or if they're different. All right, so that's a real common type of question that you guys are going to see. What else do we got? Solubility and common ions. So in the buffer unit, you guys remember how common ions work? Well, same kind of idea goes on with salts. So we're going to calculate the solubility, this time in grams per liter, of silver bromide in pure water, and then in a silver bromide solution. Now I hope you guys can make sort of a prediction here that if you know what, oh, I think my little guy is dying. That makes me so sad. If your bromine ion concentration is high, then that's going to shift the equilibrium to the left, and it should make your salt less soluble. So we'll see if the numbers work out. So for these two calculations, I would like you guys to set up some ice tables and see how it goes. So again, pause, and then go ahead and set it up, and then in a minute, continue the video and check your work. Alright, so for this first one, got a beautiful little equilibrium going on here. Initially, since we're in pure water, we don't have any silver ions, no bromine ions. So as it turns out, when you calculate your KSP, when you calculate x, comes out to 8.8 times 10 to the negative 7th, okay? And then I did convert that to grams per liter. So the solubility of silver bromide, 1.7 times 10 to the negative 4th. All right, well, how does that compare to the little silver bromide solution? The only difference is that this time, you're going to have bromide ions already present. So instead of being 0, 0, you're going to have a number here. So that's the key difference. All right, let's take a look, see how you did. So there's that number in red, and how's that going to affect the equilibrium? Just like we saw in the earlier units, plus x compared to 0.001 is not going to be significant, so we simplified the math a little bit. Calculated the gram solubility the same way, and it came out to 1.4 times 10 to the negative 7th. Okay, does this support what we thought? So if you have the presence of a common ion, if there's a lot of bromine in solution already, this goes up, okay, and then that shifts the equilibrium this way. So you have less ions, and you have more solid. So there you go. So common ion, it works the same just as it has in previous units. What else can we do here? So I want you guys to take a look at another common ion problem, but this time it's got a little bit of acid base going on in it as well. So I want you guys to calculate the molar solubility. So that's going to be in moles per liter. So again, molar solubility means you're solving for X. How much that solid will dissolve in 1 liter of solution. Okay, but this time in a solution that's at a pH of 10. So a pH of 10, well, that's basic, right? So that already implies that you have some hydroxide already sitting there, and you want to see, well, how soluble would this lead hydroxide be in this environment? All right, so go ahead again, pause, set up your ice table, make sure you put in the appropriate amount of hydroxide for your initial hydroxide ion concentration, and see if you can get this answer. All right, hopefully you guys worked at it till you got that answer. So there's our hydroxide based on the pH. So you got the POH and went from there. From there, this little guy is commonly missed, OH, then there's a 2 in front, so you have to make sure and square the concentration here. And then from there, your X comes out to 1.2 times 10 to the -7th moles of lead hydroxide would dissolve in 1 liter of solution. All right, well, I kind of gave you the answer on this one too. What if you're at a pH of 12? A pH of 12 implies more hydroxide. So that means this arrow is going to even get bigger, so it's going to shift the equilibrium even more to the left side. So that would imply that the solubility would be the solubility would be even less. All right, moving on. So that's common ion effect. Now, in class in that POGO activity, we did deal a little bit with Q. We're going to talk a little bit more about that, sort of summarize. So to precipitate or not to precipitate. So we're going to be talking all about double replacement reactions and whether or not you will see a precipitate. All right, so we're calculating Q, and just remember that Q is sort of that snapshot. It's whatever your initial conditions are, not necessarily at equilibrium. So Q is calculated the exact same way as K. So this is our summary. So if you do see a precipitate, okay, I'm thinking precipitation like snow days or something here. If you see a precipitate, goodness me, that means you have too many ions. You have too many ions, so to get back to equilibrium, to reach a perfectly saturated solution, you got to get rid of some of those ions. So to get rid of some of those ions, we're going to shift the equilibrium back that way. So that means in this circumstance, Q is going to be greater than KSP. Okay, you have Q is basically the product of these ion concentrations, and they're too high, so to get rid of them, shift in the opposite direction. So what if you mix two things and you don't get any precipitation? Well, that means Q is less than KSP. The concentration of the ions are just too low. And finally, the perfect situation, what if Q equals KSP? That means that you have just the perfect amounts of ions and you are at equilibrium, which really means that you have a perfectly saturated solution. Consequently, if Q is less than K, and gosh by golly, your ion concentrations are too low, we would call this an unsaturated solution. And this one, if Q is greater than KSP, you know what? For that moment while the ions are too high, we would call that a supersaturated solution because you have more ions dissolved than you should. But the thing about that is supersaturation never lasts because you then get rid of those ions, and you know what? You get rid of those ions, which makes it precipitate, until it's again saturated. So in all normal circumstances, after you see the precipitate at the bottom, it usually means the remaining solution is saturated. We'll talk a little bit more about that in class too. All right, so what about the math? So we have this little circumstance here where we have carbonate ions are added to a solution in which the original magnesium ion concentration is this. So we're going to keep the magnesium constant, and the question says, will you get a precipitate if the carbonate ion concentration is this much? So go ahead and calculate that, and in fact calculate the next couple. So let's see, I want you guys to calculate A, B, and C, and then come back here and check your work. So pause, do the work, and then check. Okay, so magnesium stayed constant. We popped in that value for the carbonate. If the carbonate was this concentration, this would be your Q value. Well, in this case, KSP is this number here. Q is too low. So therefore, the ion concentrations are not what they need to be. So you just basically be looking at an aqueous solution when you mix these two. All right, what if we bump the carbonate up to 0.15? All right, that's a lot more carbonates. So now Q is greater than KSP. So you got too many ions, so we would get rid of some of those ions by kicking them out, shifting the equilibrium to the left, and you would see a precipitate. One thing I want you guys to notice is, according to this equilibrium, the magnesium and the carbonate are in a 1-to-1 ratio. Are they in a 1-to-1 ratio here? Not in the least. And that's okay. It's just because the magnesium came from one source and the carbonate came from another source. They can be whatever. If your carbonate happens to be high, then maybe your magnesium is going to be low. Doesn't really matter. And finally, this question says, at what concentration would you need the carbonate to be so that you would have a saturated solution, so that above which precipitate would start to form? So this is using KSP. So if this is my magnesium, what does the carbonate have to be to basically make a saturated solution or to be at equilibrium? So it comes up to 0.068. So if you went above that concentration, that's when you're going to start to see a precipitate. And maybe you'd have a snow day and blizzard bags. Just kidding. Sorry. Continuing on. All right, so this is what I really like to do with Q versus KSP, is your classic double replacement reaction. So here we're going to react magnesium nitrate with sodium carbonate. All right, so this is the classic double replacement reaction that's taking place. You could have done that in CP Chem or even regular chem. But for us, what we really care about is what's going on with the magnesium carbonate. So this is the equilibrium that we care about, is assuming we made that magnesium carbonate, okay, how much of it would actually stay dissolved in solution? So the basic premise when you do a double replacement and you're wondering if a precipitate will happen are these 3 steps. First of all, calculate the magnesium and the carbonate ion concentrations after mixing, but before reacting. From those concentrations, that's what I want you to calculate Q based off of. So those would be like your initial ion concentrations. Then compare Q to K. Go ahead and do it. Pause the video and then check when you're done. Alrighty, so let's see. So we got the moles of magnesium divided by the total volume. This was my new concentration after mixing but before reacting for the magnesium. And this is the concentration for the carbonate. So when I solve for Q, when I solve for Q, Q comes out larger than KSP. So you indeed would see a precipitate. So when I mix these two, just like every double replacement reaction that you're used to, the solution would get cloudy and you'd eventually see a precipitate settle to the bottom. All right, that's as hard as I can make that one. This one is a little bit tricky. So the question is will you form a precipitate if you mix 2 milliliters of NH3 with iron sulfate? The question is what is this reaction? What are you going to make? So you got your iron. That's kind of a no-brainer. And I'll just like to point out that the sulfate is pretty much going to be not a factor. So what's going to come from the ammonia solution that would make a precipitate with iron 2+? See, so NH3 doesn't really participate in double replacement reactions. So hopefully in your mind you're thinking to yourself, well, ammonia is a weak base, right? So a weak base would produce hydroxide. And that's actually the equilibrium we're going for. Okay, is that these two guys would react, and indeed you could make, and by the way, my little airliner is broken, so yeah, I'm just using the computer here. It's great. That's really legible. So the iron hydroxide is the precipitate we're wondering about. All right, so basically we got a little bit of solubility stuff, but we got some acid-base stuff going on here too. So basically you would have these two processes. So we're going to get our iron from the iron sulfate, but we're going to get our hydroxide from this equilibrium. Okay, and of course, as you guys remember, that's going to be represented with a Kb, 1.8 times 10 to the negative fifth. So could you look at this problem, calculate the iron? Could you look at this problem, calculate the hydroxide, and then put it all together to calculate Q and compare to KSP and decide if there's a precipitate? I'd love to see you guys give it a try. Pause, and then go ahead and check the key in just a minute. Now, I know that you're just not, do the problem. Do it. Do it right now. I'm watching you, Just kidding. I don't want to scare you or anything. All right, so got my iron concentration. So I went ahead and just like in other Q problems, I got the ammonia concentration after it was mixed, but before it reacted. Then I took that into the equilibrium. All right, nothing fancy going on there, so I was able to calculate for the hydroxide based on, how much this NH3 actually dissociates. Pop those numbers into the Q expression, comes out to something times 10 to the negative 11th. That indeed is larger than the KSP for the iron hydroxide, which I guess I didn't actually give that to you, but it is on that sheet. I did give you guys a reference sheet with all the KSP values. It's also in your book. So Q is greater than KSP, so you would indeed get a precipitate. All right, believe it or not, that's it. So if you guys could, you do not have to worry about the last page of the notes, but I do want you to go back to the KSP POGIL that you worked on the blizzard bag and just perfect all the problems that you did. It should make a lot more sense now. And don't forget that the answers are posted on Edline. So on Monday, all these notes should be done except for the last page, and the POGIL should be perfect. Hope you guys enjoy your weekend, and we'll see you on Monday.